If you're in any kind of science, engineering, or data science field, you've definitely used Python, right? But here's the thing you might not know. Underneath so many of those powerful tools, there's this one foundational engine. It's been quietly shaping scientific computing for more than 20 years. So today, we're going to pull back the curtain on that engine. SciPy.
All right, so here's the game plan. First up, we're going to look at the total mess that basically forced SciPy into existence. Then, we'll get into the brilliant blueprint it shares with NumPy. After that, a quick tour of its most powerful features. We'll see how it's the engine for the entire Python ecosystem. And finally, we'll peek into the future and see how it's staying ahead of the curve.
Okay, so to really get why SciPy is such a big deal, you have to rewind the clock. Think late 90s, early 2000s. Scientific Python, it was the Wild West. Super exciting, yeah, but also a total mess of different tools that didn't talk to each other. And that fragmentation, it was about to explode into a real crisis.
And this timeline here, man, it just captures that chaos perfectly. So in 95, you get numeric, which was the first real array for Python. Big step. But then by 2001, this new kid on the block shows up, numarray, which was way more flexible. At the exact same time, a few developers, Travis Oliphant, Eric Jones, and Piru Peterson, they merge all their code and create SciPy, but they build it on the older numeric library. And just like that, boom, the community splits right down the middle. You had two different camps, building on two totally incompatible foundations. I mean, it was threatening to kill the whole scientific Python dream before it even got off the ground.
And listen, this wasn't just some friendly technical debate. It was, and I'm quoting the early developers here, an unsustainable tension. This fractured community was a genuine threat to the whole idea of open source science in Python. It was a breaking point, and it's exactly what forced them to come up with the brilliant solution that we still use today.
So how'd they fix it? Well, out of that total mess came an architectural blueprint that was so good it's still the gold standard. And it all began by fixing that deep split between the array libraries.
The solution? It was the creation of NumPy. It took the best ideas from both numeric and numarray and rolled them into one solid package. And its absolute core, the heart of it all, is this thing, the ND array. You can just think of it as a super efficient box for numbers. It's the bedrock. It's the fundamental Lego brick that everything else is built on. And this slide just perfectly lays out the division of labor. NumPy gives you the fundamental nouns, that's the ND array, and the basic verbs you need to move them around. But SciPy? SciPy takes that foundation and gives you the paragraphs. We're talking the complex, high-level scientific algorithms for stuff like optimization, signal processing, and heavy-duty stats. They're two sides of the same coin. You literally cannot have SciPy without NumPy.
Which, brings up a really important question. We all know Python is easy to use, it's great to write, but it's not exactly famous for being fast. So how in the world does a library built on Python compete with speedy, compiled languages like Fortran or C?
Well, the secret is that SciPy is this incredibly clever wrapper. Look at how this works. Your simple Python command, that's just the tip of the iceberg. Under the hood, SciPy acts like a translator. It takes your request and immediately hands it off to this battle-tested code written in super fast languages like Fortran or C. That's where the heavy lifting happens, at blazing speeds. And then, SciPy just hands the result right back to you in Python. It's the absolute best of both worlds. You get Python simplicity with the raw compiled power.
And we're not just talking about some random compiled code here. No way! SciPy is wrapping the absolute legends of numerical computing. I mean, these are libraries like BLAS and LAPACK. They've been optimized for decades, and they are the foundation for tons of scientific software, even commercial stuff like MATLAB. SciPy's real genius was making all that power available to anyone for free through a nice, clean Python interface.
Okay, so now that we get the architecture, let's take a quick spin through the toolbox itself. SciPy is really organized as a bunch of powerful submodules, and each one is designed to tackle problems in a very specific scientific area.
And this is really just a taste of the arsenal SciPy gives you. Seriously, think of it like a garage full of specialized toolboxes. You need to solve some nasty matrix problems? You grab scipy.linalg. You're working with calculus or differential equations? That's what scipy.integrate is for. Each one of these modules is just packed with the specific high-level tools you need for that job.
And here's something you really need to get about SciPy's whole philosophy. There is no magic bullet. There's no one-size-fits-all algorithm. Let's take scipy.optimize, for example. It doesn't just give you one way to find the minimum of a function. It gives you a whole suite of them.
Why? Because the best method totally depends on your specific problem. Do you have gradient information? Are there constraints involved? SciPy's goal is to empower you to choose the right tool for your job. And this is a fantastic illustration of that philosophy in action. The main function for solving ordinary differential equations is called solve IVP. It's one single clean interface. But behind the scenes, you can pick from a whole range of super powerful solvers. You can stick with the default RK45, which is a great workhorse for most problems. Or maybe your problem has stiff regions. That's where things are changing on wildly different timescales. No problem, you can switch over to LSODIA. And for the really tough, stiff problems you see in things like chemical kinetics, you can call in a specialist, BDF. It's all right there for you.
So all this power and all this flexibility has made SciPy way more than just another library. It's actually become the computational engine that drives the entire scientific Python ecosystem. I mean, just think about the journey your data takes. It often starts out in pandas, right? You load it, you clean it up. Then it gets converted into a raw NumPy array for some basic manipulation. But then comes the magic moment, the actual analysis, the deep computation. That's where SciPy comes in. It is the computational heart of this entire workflow. It runs the complex stats, the optimizations, and then you visualize the result in Matplotlib. It's the absolute critical link in the chain.
And its influence goes even further. Take scikit-learn. I mean, it's arguably the most important machine learning library in Python, and it is built directly on top of this foundation. It totally relies on NumPy for its data structures, and it leans heavily on SciPy for critical stuff like handling sparse matrices, datasets that are mostly zeros, and for the powerful optimization routines that are needed to actually train the models.
And for other massive libraries to rely on you like that, it all comes down to one thing: trust. And this number is 16. It really tells that story. It took 16 years for SciPy to go from version 0.1 to version 1.0. Now, that's not because development was slow. Not at all. It was a conscious decision by hundreds of contributors to put stability and reliability above everything else. And when your library is being used for reproducible science, that commitment is absolutely everything.
But hey, the world of computing never stands still, right? So for this last part, let's look at how SciPy is changing to stay essential for the next decade of science, a future that looks more and more heterogeneous. Okay, the single biggest, most important strategic move for SciPy's future is this: the Python Array API standard. See, for decades, SciPy has been hardwired to work with one specific thing, the NumPy ND array. This new standard is all about breaking that dependency. So why is this such a huge deal? Well, look at what it unlocks. By programming to a generic API instead of just to NumPy, all of SciPy's powerful, battle-tested algorithms can suddenly run on completely different kinds of arrays. You could run a scipy.optimization routine directly on a GPU array using a library like CuPy, or on a Jakes array to get just-in-time compilation and automatic differentiation. It basically future-proofs SciPy, making it portable to all the specialized hardware that's going to define high-performance computing. And this kind of modernization is happening all over the library. A great example is in scipy.sparse, which is so critical for handling data with lots of zeros. It's getting a major upgrade. It's moving away from the old spmetrics object, which could only handle 2D data, to the new esp array, which can handle the n-dimensional sparse data that you see all the time in modern AI and machine learning. So when you take a step back and look at the whole picture, SciPy's legacy is just immense. It took decades of numerical computing research, stuff that used to be locked up in expensive commercial software or hidden in obscure Fortran libraries, and it made it free and accessible to literally everyone. This democratization of science has powered countless discoveries and was even a key tool in the analysis that finally confirmed the existence of gravitational waves. Just incredible. And that really leaves us with one final thought. We're moving into an era of incredibly diverse and specialized hardware. We're talking GPUs, TPUs, you name it. In a world like that, is a universal standard like the Array API going to be the key strategy? Is that what will allow foundational, community-built libraries like SciPy to not just stick around, but to lead the way for the next generation of scientific breakthroughs?